Hey everyone, and welcome. Ever feel like math has secret rules? Well, today we're going to become detectives and uncover them. See, every function has this hidden code, a list of what's allowed and what's totally forbidden. We call that code the domain, and by the time we're done here, you'll know exactly how to crack it. So let's jump right in.
I mean, seriously, think about this for a second. What if some numbers were just illegal in math? What if plugging one in could just break everything? Sounds kind of traumatic, I know, but it's totally true. Some functions have these hidden danger zones, these inputs that cause complete chaos. So our mission today? Find those illegal numbers and figure out where it's safe to play.
And yeah, you guessed it, that safe territory has an official name. It's called the domain. So really, when we talk about finding the domain, all we're doing is figuring out which numbers are legal, the ones that are perfectly safe to plug into our function.
Okay, so here's the textbook definition for you. The domain is simply the set of all the legal inputs for a function. But where do we even start? Well, the good news is, for most functions, the default setting is, well, everything. We can pretty much assume every number is allowed. Yep, you heard that right. The default is just a total green light. Any real number you can think of, from negative infinity all the way to positive infinity, you're good to go. This is true for all those polynomial functions, things like x squared plus 5x, and a bunch of other basic functions. But, and there's always a but, right? There are a couple of major exceptions we gotta watch out for.
And this is where our detective work really kicks into gear. We have to learn how to spot the two main red flags, the things that scream at us, hey, the domain here is restricted. These are the danger zones we're on the hunt for.
Okay, here we go. These are the only two rules you need to burn into your brain for finding the domain. Seriously, think of them like the two great commandments of algebra. Red flag number 1, you absolutely cannot divide by 0. It just breaks math. So the bottom of a fraction, the denominator, it can never, ever be 0. Got it? Okay. Red flag number 2, you can't take an even root of a negative number. So like a square root or a fourth root. The stuff inside that root, we call it the radicand, has to be 0 or something positive. And that's it, I promise, just those two rules.
All right, enough with the theory, right? Theory is great, but let's see how this actually works. Let's put these rules to the test with a couple of examples. We'll start with a pretty simple one and then ramp it up a bit.
Okay, so check out our first function. Right away, what do you see? A fraction, right? That should be like a giant flashing neon sign. That's our first red flag. The second you see a variable down there in the denominator, those division by 0 alarm bells should be going off in your head.
So how do we tackle this? Let's break it down step by step. Step 1, we've already spotted our red flag, that division bar. So we're going to zero in on the denominator. Step 2, we just grab that denominator, the part that can't be 0, and we write it out. X minus 3 is not equal to 0. And step 3, well, that's the easy part. Just a tiny bit of algebra to figure out what x is.
And boom, there it is. Our answer is x cannot be 3. Think about it. If you plug a 3 in there, the bottom becomes 0, and we break that number 1 rule of math. So what's the domain? It's every single number in the universe except for 3.
Okay, ready for round 2? Let's check out this next function. What do we see this time? A square root. That's our second red flag, loud and clear. And that should immediately make you think of our second rule. Whatever's inside that root, it just can't be negative. And you know what? The process is pretty much the same. Step 1, spot the red flag. Here, it's that even root. Step 2, grab everything inside the root, that radicand, and set it to be greater than or equal to 0. Makes sense, right? It can't be negative, so it has to be 0 or bigger. So we write down 2x plus 8 is greater than or equal to 0. Step 3, let's do the math and solve it. And once we solve that, we get our answer. X has to be greater than or equal to -4. Any number in that zone is a totally legal input. But if you try to get clever and plug in something smaller, like -5, what happens? You'd be trying to take the square root of a negative and, oops, you just broke rule number 2. All right, now for the fun part, the boss level, if you will. What happens when a function throws both red flags at you at the same time? Oh yeah, this is where you get to show off your detective skills. We're going to look at a function that has a variable in the denominator and a square root. Let's do it. Okay, so check this out. Our two rules are kind of in conflict here, right? The square root part tells us that the inside, the 5 minus x, has to be greater than or equal to 0. But wait, that whole thing is in the denominator, and we know the denominator can't equal 0.
So what do? We combine them. If it has to be greater than or equal to, and also not equal to, what's left? It has to be strictly greater than 0. It can't be 0 anymore.
So that's our new rule for this problem. 5 minus x is strictly greater than 0. Now we just solve it. We subtract 5 from both sides. That gives us negative x is greater than negative 5. And now, stop! This is the most crucial part, a classic algebra trap that gets everyone. When you multiply or divide an inequality by a negative number, what do you have to do? You have to flip the sign. Don't forget it. Honestly, that sign flipping thing we just did, it's probably one of the biggest mistakes people make. So let's just take a quick second to go over a couple of common mistakes so you don't fall into the same traps. Okay, here are the 2 big ones to watch out for. First, people sometimes try to apply the root rule to odd roots, like a cube root. But that's not a problem at all. You can totally take the cube root of a negative number. The cube root of negative 8 is just negative 2. So remember, this rule is only for even roots, square roots, fourth roots, and so on. Second, just like we saw, forgetting to flip that inequality sign when you divide by a negative. Seriously, burn that rule into your brain.
So I know what you might be thinking. Okay, this is cool and all, but is it just some abstract math thing? And the answer is no, not at all. The idea of a domain is actually super important in the real world, especially in places like physics and engineering.
I mean, in physics, the domain isn't just a rule you follow, it's reality, right? If you have a function that describes something moving, you can't have negative time. It doesn't make sense. So its domain has to be time is greater than or equal to 0. An object can't have negative mass. A box can't have negative length. All these real-world limits, that's the domain. So here's the big takeaway. Finding the domain isn't just some random busy work your teacher gives you. It's literally the first step to understanding what a function is actually doing. It's like finding the map that shows you where the function is alive and where it just doesn't even exist. And that's why this is so important, especially as you move on in math. You can't do the more advanced stuff like calculus. You can't differentiate or integrate a function in a place where it's not even defined. Finding the domain is the foundation for everything else you're going to learn. And that kind of leaves us with a really interesting question, doesn't it? We know that in our first example, the function is just broken at x equals 3. It doesn't exist there. But what's it doing as it gets really ridiculously close to 3? You know, if these rules define the edge of the map, what happens when you walk right up to the edge of the cliff and peek over? Well, that is a story for another time. Thanks for hanging out with me today.